In part A of this question, we're looking at a standard question about the conditions under which we can approximate from binomial to a Poisson. So when I think about these questions, I always think, well, when would I not be able to use binomial? Well, I can't use binomial if my tables don't go up that high. So that gives me my first clue as to a condition, that n is large. Because if n is large, so large it's not in the tables, I'm going to have to use an approximation. Also, if n is large, that makes my curve nicer and smoother, which is generally quite useful. The second thing I need to think about is whether p has to be close to 0.5 or it has to be close to 0. I know it's one of the two. What I'm going to think of is the fact that Poisson distributions go on for infinity, so inevitably they're going to have their peak quite early on like that. Also, something we know about Poisson is that the mean and the variance are the same. Now think about that for a binomial. In a binomial, the mean is np and the variance is np times by 1 minus p. Now I want those two, this and this, to be close to each other, because that's what happens in Poisson. So if that's what happens in Poisson, I want to approximate to Poisson, I need these two values to be close to each other. That is only going to happen if p is small. Because if p is small, this bit here, the 1 minus p part, is going to be close to 1. And if that's close to 1, then we're basically multiplying this, which is the same as this, by 1. Anything multiplied by 1 is itself. So the only case in which this can be similar to this is if that p there is very small, which inevitably means, of course, that p there and that p there all have to be very small. So if p is small, that's the other condition for which we can go from binomial to a Poisson. Part B, we're doing a hypothesis test. Now, I need to figure out, first of all, what is my distribution, and second of all, what is my test statistic, so I can think what numbers go where. Well, I'm thinking for my distribution, it looks like a binomial where I've got 200 as my number of trials and 3% as my success or failure. So that's the first thing I'm going to write down. X is a binomial distribution with n is 200 and p is 0.03. And 12, I'm not going to be using right now. I'm going to save that number for later. That is what I'm testing against this distribution here to see how unusual is it to get 12 if this is true. That is what I'm doing. I'm seeing how unusual is it to get 12 defective bolts if it's true that we're using this machine where only 3% is usually defective. So let's think now about how I'm going to set up my hypothesis test in terms of my H0, my null hypothesis, and my H1, my alternative hypothesis. My H0, my null hypothesis, is always that nothing has changed from my initial distribution. So in this context, it means that P is still 0.03. Nothing has changed. My alternative hypothesis, however, I need to look to the question to see what change they're asking about. They are asking whether the proportion of defective bolts is now higher. Higher is telling me I want to test whether P is now greater than 0.03. So, what does this tell me so far? It tells me that I've got a one-tail test because this greater than sign, I'm only testing one end. I don't want to see whether it's less than or greater than. I just want to see if it's greater than. So that's a one-tail test. And going back to the question up here, I can see that I have a 5% level of significance. Right, once I've written all of that stuff, that is when I can start then looking at my test statistic. I can start thinking about this number 12. What relevance does that now play? What I'm testing is whether 12 is such an unusually high number for this distribution that it puts me in the top 5% of the population. If this is my top 5%, where exactly does 12 on the x-axis here, which is the number of faults, where does that put me? Does it put me here on this side, in which case it's not in that most extreme 5%? Or does it put me more like up here, in that shaded region, such that it is in the most extreme 5% of values? It's incredibly unusual to get 12 faults. We don't know that yet. We need to look up in order to figure out whether it's more like here or here. We need to be looking up the probability of x being greater than or equal to 12. Remember, 12 was our test statistic up at the top. So we're seeing, is 12, would that put us there, or would it put us more like here? Now, here's a problem. I have a distribution where n is 200. 200 I can't look up in the tables. Well, what am I going to have to do? I'm going to have to approximate, going away from binomial. My p is small here, so that tells me Poisson is my best bet. How do I go from a binomial to a Poisson? Well, Poisson has a lambda of np for a binomial, so I've got to do 200 times by 0.03, which will mean I now have a Poisson distribution with a lambda of 6. Right, I now need to use my tables to look this up. I need to look up p of x being greater than 12 in my Poisson tables when lambda is 6. I can't look up greater than or equal to in my tables. I can look up less than though. So I'm going to find the equivalent using less than, which is going to be 1 minus the probability of x being less than or equal to 11. That comes out as 0.0201, which is equal to about 2%, 2.01%. What does that number actually mean? Let's stop and think. What that number means is that 12 is in the position in this distribution such that the area above it, because remember I was looking at greater than, the area above that curve is just 2%. So it's really squished up the top here, so I've only got 2% of the whole of this area of the distribution above it. That makes it extremely unusual to get 12 or higher. It's in this case, because that is lower than 5%, that we conclude that it's so unusual we actually want to reject the idea that nothing has changed. So we need to write the following. 2.01% is less than 5%, which means we reject H0. We reject the null hypothesis. And then to get the final mark, we need to put it in the context of the original question. Let's scroll back up to see the original context. We were looking at the proportion of defective faults, whether that is higher with the new machine or not. Well, remember, this is a distribution for the old machine, and it was incredibly unlikely that we would have got that with the old machine. There's only a 2% chance that would have happened with the old machine. We now need to write that up for our final mark. So we're going to say it very, very precisely indeed that we believe there is evidence that the proportion of defects has increased. Now, I would always recommend that you pick out this wording directly from the original question. Don't get smart, don't try and overcomplicate things. we are being asked specifically about this case about proportion, defects, and whether it's increased. So I've stolen those words. Make it easy for yourself. Once you've written that final sentence, the question is done. You've got full marks. Well done. Move on.